In the last video, we talked about what it means for some kind of a function or an operation to have linearity. And then we proved that for any general second order linear differential equation, which we named an operator on a function y, that this has linearity because the property is satisfied that if we plug in to our operator, our differential equation s, if we plug in some constant times a function plus another constant times a different function, that's the same as the first constant times the first function plus the second constant times the second function. That is linearity. Now, as just one more stepping stone before we begin to solve our second order linear differential equations, I had to talk about the concept of linear independence. So what is linear independence? Because it's going to prove useful for us to actually, if we want to be using this property that we have k1y1 plus k2y2 is k1 s of y1 plus k2 s of y2, if we want to use this linearity, we're going to have to explore where it's not so useful to have this. And the area where it's not useful is if y1 and y2 are what is known as linearly dependent. Okay, so what does it mean to have a linearly dependent set of functions? Well, to begin what linearly independent and linearly dependent mean, let's actually think about vectors. If I draw myself a graph, and I just figured out how to use the shift key in this program. It's very nice. I can do very straight lines now. If we have an x-axis and a y-axis, and we have some different vectors, we might intuitively know what linear independence means. If I draw out some kind of a vector here, and I draw out a different vector in this direction, these vectors are certainly linearly independent because they don't stack on top of each other. Together, we could add scalar multiples of them to reach any point in the plane, and the only way they're ever going to equal 0 is if both of their scalar multiples, so if we're thinking about ways that we could multiply them to make them longer, right? So we have like another, we make it however much longer we feel like. If we're thinking about ways to make it longer, the only way to get these two to add to 0 when they're multiplied by different scalars is if both of the scalars are 0. So the only way to get them to 0 is if we actually shrink them, put each down to 0. In math, what that means for vectors at least is that if we have some constant c1 times, if this is u and this is vector v, c times u plus a different constant times v, this equaling 0 if they are linearly independent. So if linearly independent, which I guess I'll shorten to linearly indep, if linearly independent, then this equaling 0 implies that c1 and c2 themselves equal 0. And if they're not linearly independent, then there might be some combination of c1 and c2 where this actually will equal 0 without c1 and c2 equaling 0. So to see that, let's look at another example where we'll have actually linearly dependent vectors. So let's imagine x-axis, y-axis. We have some kind of a function here. Not a function, sorry, a vector. So we've got our vector. And we have another vector, which I'll do in orange, which is linearly dependent to this vector. Now, what we might notice about these two vectors is they're right on top of each other. If this is the vector u and this is the vector v, there's really no breathing room. If we imagine this scalar addition equation, there's clearly a set of c1 and c2 where this will equal 0 without c1 and c2 equaling 0. Namely, if c2 for v is just 1, we keep v as it is, and we say c1, make it exactly negative so that u is exactly negative of v, then we can scale u up to be, wrong color, we can scale u up to look like this, and then when we add it with v, we're going to get 0. So clearly this isn't linearly independent, and therefore we call it linearly dependent for vectors at least, if they're stacked right on top of each other. And although the intuition doesn't extend perfectly from vectors to functions, the concept is still the same, and we still have it so that if this expression is 0, then two functions are linearly independent if c1 and c2 equaling 0 is the only solution. So let's rewrite this for specifically now functions. So if we have a function f1 of x, and f2 of x, if we say we have some constant times f2 of x, which I guess I'll call c2 times f2 of x plus c1 times f1 of x, and we add them together, and they equal 0, these two functions are linearly independent. So linearly independent if the only solution for this is c1 and c2 equals 0. So it's implied, and it is implied by c1 and c2 equals 0 as the only solution. Even if they were linearly dependent, this would obviously still be a solution. So the only solution. So like for this u and v, even though they are linearly dependent, there is still the solution if both constants equal 0. But if it's the only solution, then we know for sure that these two functions are linearly independent. So let's look at an example of two linearly independent functions, and then an example of two linearly dependent functions. So let's give ourselves some room. I guess let's keep our definitions up. Okay, so if we had that we have f1, let me do a little higher, f1 of x equals 2x, and f2 of x equals 9x, we can show that these two functions are linearly dependent. So these are dependent on each other because they have these two x's. So if we say c1 times f1 of x, which is 2x, plus c2 times 9x equals 0, there's clearly a solution here, because we have, if we factor out x's, we have x times 2c1 plus 9c2, which also, because these are arbitrary constants, we can just absorb those factors in. We have c1 plus c2. Clearly, if we chose the correct constants here, we would be able to get it such that this value is equaling 0. So we wouldn't necessarily need it so that c1 and c2 were 0. For this equal 0, we would just need specifically c1 equals negative 9 halves c2. So these are clearly dependent functions. But what if we had instead two functions that were more like f1 of x? Let's keep it simple. f1 of x is the same, is 2x. But f2 of x is now going to equal the cosine of x. All right, now if we write this out, what we get is c1 times 2x plus c2 times the cosine of x, that this equals 0. So I don't know about you, but I don't think this has any solutions for this here, where c1 and c2 aren't 0. So what we would say is these two functions here are linearly independent. And the whole idea of linear independence should feel fairly comfortable, because cosine of x and 2x are wildly different functions. On the one hand, we have 2x, which is that function, and on the other hand, we have the cosine of x, which is this function, where it goes up and then down and then up, and they're not scalar multiples of each other. So in general, they won't be able to be made 0. Okay, so, oh, and I suppose one thing that I should have said also is that this has to be true for all x. So it's not just that you can find one value of x, but it must be for all x. So obviously if I had said that this function here was the sine of x, we would have had one value here where both functions were 0. So that would have meant that at 0, even though sine and 2x are obviously just as linearly independent as 2x and cosine of x, that at 0 we would have had f1 of x times some constant plus f2 of x times some constant. That would have been some constant times 0 plus some other constant times 0. Obviously that would have equaled 0. But you need it to equal 0 for all of your, so we need 0 for all x. And that is the condition for being linearly independent. And just quickly, if we're going to return to differential equations for a minute, the reason that linear independence might be useful is because it says if we have this s of y, this operation that takes in a function and then spits out your side of a differential equation, that if you have two linearly dependent functions, this really isn't very useful, because what it means is that k1 y1 plus k2 y2, if y2 and y1, if y1 and y2 are dependent on each other, then it's really not that exciting to say that some constant plus some constant of y1 plus some constant times y2, that this equals this. That isn't very exciting because it falls right out of being linearly dependent. So what we're going to care about is where y1 and y2 are actually independent. This is going to be the exciting case because when y1 and y2 are independent, this property of linearity is going to give us a way to combine solutions. And just as a quick foresight for what we're going to do, imagine a differential equation where you found some solution. So you found some solution, y1, to this differential equation, such that s of y1 equals 0. So you found a solution where you plug it into the differential equation, and you always get 0. And imagine you found a different solution, y2, where your differential equation was some function, like f of x. And you wanted to solve the differential equation for all functions where when you plug in the function to s, you get f of x. Well, imagine this. If y1 and y2 are linearly independent functions, and this holds, then another solution to s of y2 equals f of x, another solution to that is going to be s of y1 plus y2. Because we can separate this out, the y1 part will go away after evaluating the s, and we're left with y2. Okay, so little foresight aside, we now know what it means to be linearly independent. And as we're going to see, it's going to be very important to showing if this is actually meaningful for two given functions. See you in the next video.